So in this video, I want to explain the way selection sort is sorting an array. The idea of selection sort is pretty simple. It tries to find out initially who should be at this place if this array is ordered. In order to find this element that should take this place, well, it has to walk through the whole array and find the minimal value. And since if this element is found and determined, so in this case the minimal element would be here, this element is swapped with the element that just takes this place. So in the first phase of this algorithm, it would determine that this is the minimal value and it would exchange these two elements in this array. So that's the idea of selection sort. And if you have found this minimal value and exchange that, then you can just proceed with a second element. Then you're looking for the element that should take this place. And you see on the simulation, again, we have this yellow bar. And the idea of this yellow bar is, okay, again, we have two parts of the array. One part is already sorted. Everything that is left to this yellow bar is sorted. And even more, it's already in its flying place. That is the difference between selection sort and insertion sort. So if something is left from this yellow bar, we know, okay, it won't change its place anymore. So if we start now with the simulation, you will see, we have three integers or three indices. So I is just place the position of the yellow bar, saying, okay, nothing is already in its final place. M is the element that is the current minimum found on the right part of this array. So, and J is the position that is just under consideration. So what we are doing initially is we set M to the position of I, so M and I are equal initially, and J is set to I plus 1. So we just make this first step, and suddenly so we have J here. And what's happening in here now is that we have an inner loop. So within this inner loop, we just walk with this J index through the whole rest of the array, the right part of the array, and check whether the element under consideration, so the jth element now, is less than the element that we believe to be the minimum of the right part of this array. So we have this while loop that just walks to the end of the array here, and if we make a step, then we just with this line we compare the jth element with the mth element, with the minimal element, and so we have this comparison symbol here, and if this is true, then we would change this m position, so this m index. So actually this is not less than this value, so we just proceed. We don't do anything, and we just increment the j and consider this element now, and we do the comparison between this element here and that element here. And again, it's not less, so we just shift the j. This next one is not less than the mth element, so we just shift the j, and so on. So we shift it, and we shift it here, we shift. So we made a lot of comparisons already and have actually not done any exchange. So now something happened, something more interesting happens. Now we consider this element here, and actually this is less than the element that believed to be the minimum. So since we now have found something that is even less, we just change the value of min, so this is the m here, to the position of j. So in order to just remember the position of the minimal value that we have seen so far. So now m is here, and then we move j to the next element, and we proceed. So if j has reached the end of the array, so now it's here, so then we will leave the inner loop. And if we leave the inner loop, then we certainly know that the position of m is just the position of the minimal element in the rest of the array, and well, then it's easy to see that we just exchange this minimal value with the element that just takes this place of the minimal value, and then we do just a simple exchange, and suddenly the minimal value has its final position. And since this now has its final position, we just increment the I. So now we have this yellow bar moved towards the right hand side, to the right end of this array, one step towards the finishing of this algorithm. So what you see here now is this yellow bar, this vertical yellow bar, it just says, okay, we won't touch this part of this array anymore. And what you see here is yet another yellow bar that just gives you some information, namely that all elements on the left-hand side are less than this yellow bar, and all other elements on the right-hand side are greater or equal. Yeah, so here we have elements which are just less or equal, and here we have elements which are just greater or equal than this yellow line here. So with the next loop, well, we proceed. We start initializing M and J. So M is this element, and J is the element that we compare with this M element in the next step. So we do the comparison. Okay, we are looking now for the smallest element in the rest of the array. This will be here. Yeah, it's quite obvious to see. So, but the algorithm doesn't know. So at the moment, it just believes that this is the smallest element in the rest of the array. So now it will update its knowledge, because now it knows, okay, this one is the element that is the smallest it has seen from here to here. Okay, so now it updates this M again. So this element here is the smallest that it has seen from here to here, and so on. We walk through the whole array, and finally we make an update here of M, and then suddenly M has this index position, and at the very end J has reached the end of the array. And if this is done, we do the exchange of the element that was the smallest that we have found when we walk from here to here. And actually now we do the exchange, then we increase the I, and suddenly the yellow bar here, the vertical yellow bar, has moved one step towards the end of the array. So again, well, this is sorted. This part of the array won't be touched anymore in the future of this algorithm. This part will be analyzed in the rest of the sorting algorithm. So now we can do this in the simulation and to try to understand what are the properties. So actually the properties are here. So again, it scans from left to the right, as Selectionsort does. The outer loop has two invariants, namely first, the elements of the to the left of the yellow bar, so the vertical yellow bar, are sorted in their final position, so they won't be touched and changed and compared anymore. No element to the right of the yellow bar is smaller than any element to its left. So this is meant by this horizontal yellow bar. So these elements are all greater or equal than the elements that are found here. So there's no need to compare them anymore, because by construction we know that this is the relation between them. And you see how it works. And the inner loop has the job just to determine the minimum of the elements to the right of the yellow bar. So that's the purpose of this inner loop here. Here we have the inner loop. So this is this is the part of the inner loop. Yeah. So it's a very easy or easy to understand sorting algorithm. And if you look at the properties here, you see, okay, the best, average, and worst cases are all equal. Yeah, so there's no difference. And if you compare this to insertion sort, well, actually, this is not a good performance. So the number of comparisons needed by Selectionsort is actually as high as the worst case for insertion sort. Yeah, but in the complexity video that is available, I will explain what are the benefits of selection sort.